Hi, and welcome to 11.4 Electrical Energy and Power. Yes, we're going to be talking about power again. And as you remember, power is equal to work over time. But how does that translate to voltage, current, resistance, all these electrical things we've been talking about? And what is with the reference table? If you go to page 4 of the reference table and you look towards the bottom of this list, look at this. Look at all these equations for power and even electrical energy or electrical work being done. That's a huge list of weird looking equations. Where do those come from? So first I'll show where those equations come from, and then we could talk about how they apply to the worksheet that we have there. So first of all, let's try to derive a formula for power that has to do, oops, that is some random stuff that keeps popping up. Hopefully that's the last time. Okay, so power is equal to work over time. And then we also have this, we talked about potential difference being the work per unit charge. We talked about current being how many coulombs of charge pass through every second. And we even have an equation for resistance, really in like a wire, rho L over A. But when we're talking about power, we're going to first derive it using the first two equations that we have for voltage and current. So as you can see, there's a work here, there's a work here, there's a time here, there's a time here. There must be some way we can relate these equations together. So let's see. Okay, well, there's two ways to think about it, right? So if you wanted to, you could solve in the voltage equation. Work is equal to the voltage times the charge. And in the, let's solve for time now. So if we cross multiply, Q is equal to I times T. And that means that T is equal to Q divided by I. And now we have an equation for work or electrical energy and an equation for time that are in terms of our electricity stuff. So we have voltage, charge, and current. So let's plug in the work and the time for the work and the time over here and see if we can make a nice formula. So we said work is equal to voltage times the current, a volt coulomb, and then the time, so work divided by time is equal to charge divided by the current. So we're just purely doing a mathematical manipulation, derivation to see what we could come up with. Well, we have an improper fraction here, so the way we deal with improper fraction is to keep that, change the division to multiplication, and then we'll flip I over, oops, let's see, almost made a mistake there, Q, oh no, we gotta flip it. Yep, Q over I becomes I over Q. Keep, change, flip. All right, and now we can simplify this a little bit more. As you can probably see where this is going. The Q's cancel out, but just so you know, if you're multiplying fractions, you do the numerator, so the voltage times the charge times the current, and then you multiply the denominators, 1 times the charge, like that. And now we could see maybe a little bit more clearly. I just wanted to show these do cancel out, and you're left with power is equal to voltage times current. So this is a useful equation for power. Still just as good as that one, but the benefit of this is that it's in terms of our electrical, physical properties. By the way, the kind of more clean derivation you could do, you could say, oh, well, power is equal to work times work divided by time. How can we get those two quantities? And you could just kind of look at the voltage and the current equation and kind of think, well, maybe if I did the voltage times the current, that would give me what I want, because we have work over time. Is that really equivalent? Let's see. Work over charge, that's voltage. And then the current is the charge per time. Would that give us what we want? And the answer is yes, the charges still cancel out, and you're left with work over time. So that means that this is a valid equation. So that's kind of like a more clean derivation, but if you wanted to kind of plug in stuff and cancel out, that's a lot of fun too. So that tells us where this one piece of information comes from by doing that derivation. And all the other pieces come from Ohm's law. And actually, as soon as you know this line, then you could just do, well, power is equal to work over time, right? So work is equal to power times time. And every equation that you have for power, if you multiply it by time, that's what it, power times time, that gives you the energy. So this times time, this times time right there. So that's kind of how those work. But so I could show where the all the different power equations come from. And I said that we used Ohm's law. So Ohm's law, as you remember, is this one. So how can we use that to derive those weird looking formulas? Well, we know that power is the voltage times the current, right? So all you have to do is manipulate Ohm's law. R is V over I. I is going to be V over R. And V is equal to I times R. So you just plug in each version of the formula. So let me show you what I mean. If voltage is I times R, you just plug in I times R for the voltage. That becomes I times R. And then you have to also multiply times I. So the power becomes I times I is I squared R. And that's one of the weird looking equations. That's where it comes from, is from Ohm's law. Now let's manipulate the same formula, but instead plug in what we know for I. Well, I is equal to V divided by R, so we plug that in. P is equal to, keep the voltage there, and we're just replacing the I with V divided by R. And now we can see we have P is equal to V times V, V squared divided by R. And I think that should be all of them. Let's check. So we have a power equation that does not have R. This equation doesn't have the voltage, and this equation doesn't have the current. So if you're given a situation where you don't have the current, then I would use this equation to find the power. So the guess method is going to be another helpful thing to look at when we're solving these. So as we can see, you could write the formula like that, and then it's just I squared R, and then V squared over R. And let's see if we did it in the same order. Yes, we did. Okay, so that's what it looks like on your reference table. It's basically like 3 different formulas in one. And now I could show where that work one comes from. It's not too bad. So we said that power is equal to work over time. And if they want you to find the electrical energy, you're going to do the power times the time. Well, work is equal to, okay, power times time, which is equal to, power is equal to voltage times the current times the time. Power is also equal to I squared R times the time. If you multiply by the time, you get the electrical energy. Power is also equal to V squared over R. Power times time gives you the electrical energy. And that's where that long string of equations come from. That one it's showing you 1, 2, 3, 4 different equations. So now we have a lot of tools in our tool belt, and we can start doing some problems. So the first question is kind of like a little tricky. It says, if the potential difference, the voltage, applied to a fixed resistance. Okay, so they want to keep the resistance the same, and you're doubling the voltage. What happens to the power? So this is another relationship type problem. We've seen these before. There's an extra thing to worry about. So it's saying, what's the relationship between voltage and power? But they also want you to keep the resistance the same. Let's see if we could find an equation, a relationship between voltage and power. Well, here I see voltage and power, but I also see voltage and power over here. And as you can see, it's a different relationship in each equation. In the first one, it's a direct relationship, but here the voltage is being squared, so it's an exponential relationship. So which one are we going to use? If you're doubling the voltage, does the power double, or does the power multiply by 4? And that's where that third piece of information comes in. They wanted you to keep the resistance the same. So it's not just voltage and power. They want to make sure the resistance is in the equation. In this equation, the resistance isn't there, so it might vary depending on which variable you choose. You could possibly change the resistance. So if you want the resistance to be fixed, and you want to know if you double the voltage, what happens to the power? 2 squared is going to be 4 times as big. That's where that comes from. So it quadruples, because P is equal to V squared over R. We want to use that R. 2, for which quantities are values needed to calculate the amount of energy? Energy is going to be like W, the electrical energy, supplied to an operating toaster. So they're saying it's an electrical toaster, it's electrical energy. Which quantities are needed to calculate that energy? Okay, so as you can see from all of the equations, they all have time. You need to know what the time is to calculate the energy. So any of these options that don't have time, that's no good. C is no good. But B and D both have time. So let's see what we got. They both have the voltage. And then, B is just the voltage and the operation time. No, that's not going to help us, because for this one, if you have the voltage, you also need the current. And for this one, if you have the voltage, you also need the resistance in addition to the time. So let's see if D makes sense. The voltage, the current drawn, and the operation time. Oh yeah, I could use VIT to calculate the electrical energy. Okay, number 3. An electric circuit contains a variable resistor connected to a source of constant potential difference. Which graph best represents the relationship between current and resistance in this circuit? Okay, so it's another relationship problem, but now we're looking for a graph. They want to know between current and the resistance. So that's I. How is I related to R? And it's a constant potential difference, so also V is being held constant here. So that has to be part of our relationship, the equation that we're going to look at. And these are the key players here, all right? So we're going to use Ohm's Law, and we want to use a version of Ohm's Law that relates current to resistance, meaning I like to have them on opposite sides of the equal sign. So we wouldn't want the current and the resistance to be on this side. I mean, you could try to figure it out based on that, but typically we'll have them on opposite sides of the equal sign. And in both equations here, it's showing the same relationship, an inverse relationship. So this is showing exponential, this is a direct, this is just like a constant relationship. I don't even know it, but it's A. A is showing an inverse relationship. Okay, number 4, it says which graph best represents the relationship between the electrical power and the current in a resistor that obeys Ohm's law. So that's key. That's like a little hidden information. If the resistor obeys Ohm's law, they're telling you the resistance is constant. The resistor isn't going to change its resistance at all. You could have variable resistors, but this one obeys Ohm's law. You want to make sure R stays constant. Sorry about that. I don't know what's going on there. So we need R, we need power, and we need the current. It's really asking the relationship between power and current, but they're saying, okay, make sure R stays the same by including it in your formula. So of the 2 equations for power that have current in it, which one would we want to use? We're going to use this one because it has the resistance. And you can see it matters because in this equation, it's a direct relationship. But in this equation, it's going to be an exponential relationship. So that's what they're telling you. If it says the resistor obeys Ohm's law, they're telling you make sure the resistance is in your formula. And then we use that one and we say, oh, it's going to be a exponential relationship. Okay, this is saying the graph to the right shows the relationship between current and potential difference for 4 resistors. Which resistor has the greatest resistance? So the graph is voltage or potential difference versus current, and they're asking for the greatest resistance. Well, we have to find how's the resistance related to voltage and current. And Ohm's law, R is equal to V over I, says it's like that. And the slope, the change in Y over the change in X. All right, so that's equal to the slope. So the resistance is the slope of this voltage versus current graph, right? Because the voltages are on the y-axis and the current is on the x-axis. So the greater the slope, the greater the resistance. So we want the one with the greatest slope or the steepest slope, and that's why It's choice A. Wow, that was a lot of relationship type questions. Now it looks like you're just going to be plugging in a bunch of numbers. So practice using the equations. So we're going to do the guess method. All right, so a 3.6 volt battery is used to operate a cell phone for 10 minutes. So T is equal to 10 minutes. But we don't like minutes. We want to make that into seconds. So times, let's see, 60 seconds per 1 minute. That's really what you're doing. You could probably do it in your head, but that's 600 seconds for 10 minutes. If the cell phone dissipates 0.064 watts of power, so P is equal to 0.064 watts, what is the current? So they're looking for the current. Okay. Well, they tell you the power. They also tell you the time, and we went through the trouble of, I just automatically converted it to seconds. But if they're telling you the power, they're not telling you what the electrical energy is. And the electrical energy, or work, is the one that we said in number 2. We were like, oh, the time is super important for that one. But we don't care about the time right now. We're dealing with power. So actually the time is what they call a red herring. It's there to try to trick you because there's so many equations to worry about. So let's see. We're really worried about power. We're definitely worried about current. We want current to be in our equation. And the voltage. So let's see, what's that relationship? If we wanted power, current, and voltage in an equation together, it's just this one. Do we need to know time? No, we don't. But if we wanted to, we have the voltage and the current and the time. We could calculate the... Oh, actually, we don't have the current yet, but we'll get it. We could do this, though. We could calculate the electrical energy if we really wanted to, if we're super curious. But that's not what the question's asking for. So the fact that they gave you the time, again, is they're just trying to trick you there. You just do the power is equal to the voltage times the current. So if you wanted to, you could solve now. I is equal to P over V. If you wanted to be fancy about it, 0.064 watts. Again, that W stands for watts, not electrical work or energy. Divided by the voltage, 3.6 volts. And you're going to get 0.017 repeating amps. Or if you wanted to be super fancy, 1.78 times 10 to the negative 2 amps. Okay, let's see. This one says an electrical appliance draws 7 amps of current, so I is equal to 7 amps. When connected to a 120 volt source of potential difference, what is the total power dissipated by this appliance? Dissipated just means like used. What's the power being used by this appliance? So P, V, and I again, you substitute in, and you get a power of 840. Watt is the unit of power. That's right. It is. Okay. Number 8. While operating at 120 volts, an electric toaster has a resistance of 20 ohms. What is the power used by the toaster? So now we're going to have to find a different equation. If it's helpful, we could see, well, what's not there? What don't we care about? So we have the voltage and the resistance. We don't have, and they're not asking for, the current. So with this long list of equations, it might be helpful to look and see which one doesn't have current. Okay, so you could see this one has current, can't use it. This one has current, can't use it. This one doesn't have current, and it has the voltage and the resistance, which is what we wanted. So we're going to use that version of the power equation. P is equal to V squared over R. We'll substitute in, and you get 720 watts. Okay, number 9. What is the resistance? Okay, so they're looking for the resistance of a 60 watt light bulb. Okay, 60 watts. So they're not telling you the power is 60 watts, but they're telling you a number with some units of watts. So you have to realize, oh, 60 watt, that's the power. And the voltage is 120 volts. So kind of similar to this previous one. We have the voltage, we're looking for the resistance, we have the power. It's going to be the same equation. But now it's a little different because we're solving for the resistance. You can solve for the resistance in your equation as is, or you could plug in now and then solve. Either way, why don't we plug in? I did the other way before. Okay, so 120 squared, and we're solving for R. So I would cross multiply, so you get, and what's 120 squared? 14,400. We're cross multiplying, right? So that times 1, and then 60 times R. So you take that big number and you divide it by 60, and then that'll tell you your answer, which is 240. Oops, my hand moved the screen. 240 ohms of resistance. All right, number 10, how much energy? Okay, so how much energy is dissipated? If they're looking for energy, they're looking for this capital W thing, which is different from this W thing. That's for watts. This is for electrical energy. And it even tells you, did you know on the right side of the reference table, it tells you what all these things, all these letters mean? And sometimes it's a good place to look if you're like, what is this question even asking me? Look over here and maybe you'll see it says electrical energy over here. That's a hint that we're going to have to look for the capital W for work or electrical energy. That's different from the capital W for watts, which is the unit of power. Okay, so now we're looking for this. We're going to use this line of equations. Let's see what else they tell us. Okay, so they're telling us how much energy is dissipated in 5 seconds. And then it's a 12 ohm resistor. And the current, okay, so the current is equal to 0.5 amps. Wow, not a lot of room to work here. Okay, so we have resistance, current. They don't tell you the voltage. They're not asking for the voltage, so you definitely don't want voltage in your equation. Let's look at this long list of equations for energy and see which one we want to use if they tell us the time, resistance, and current. Okay, so time, resistance, and current. A little bit of information overload with this big long list of equations. Again, we're looking for something that doesn't have voltage in it. Well, this one doesn't have voltage in it. Oh, but it doesn't tell us the power either, so we can't use that. This one has voltage in it. Wait, I confused myself. Hold on. Okay, yeah, we don't want voltage. So this one's no good because we don't know the voltage. Maybe this one. Not this one. So actually, this is our only choice that we could use, and it's good because they tell us the current, they tell us the resistance, and they tell us the time. So we're going to use I squared RT. And now we could plug in. We're looking for the energy. I is equal to 0.5. Don't forget to square it. The resistance is 12, and it's for 5 seconds. So how much electrical energy is that? That's going to be 30 joules of electric energy. Okay. Oh, and I should have asked, what are the units for electric energy? Okay, well, it's still like a W, which reminds us that it's work. And if you do a lot of work, you could buy a lot of joules. Do a lot of work, you could buy a lot of joules. Still holds true. Energy is in joules. Okay, an electric heater operating at 120 volts has 20 ohms of resistance. What's the total amount of heat energy, so it's still energy, produced by the heater in 1 minute? So the time is 1 minute. We said before we want it to be 60 seconds. And now we're looking for an equation that doesn't have I. So this one we don't use. This one has I, we can't use it. This one has I, we can't use it. So we have the voltage, the resistance, and the time. We're going to use V squared T over R. So that's the equation we're going to plug in. Don't forget, time needs to be in seconds, so you change 1 minute to 60 seconds. And you get 43,200. What are the units for electric energy or heat energy? It's going to be joules. And that's a weird long number, so we convert it 4.32 times 10 to the 1, 2, 3, 4 joules. Okay. Number 12, how much time? So they're looking for the time. That's a hint. We'll probably have to use that the W formulas for the operating 100-watt light bulb to dissipate 12 joules of electric energy. So again, electric energy is the W, or the work that it's doing, 12 joules. So this is actually, you might feel a little nostalgia here, back to Unit 8 when we were talking about work, power, and energy. It's our good old power formula. And why are physics students the most powerful students? Because they work overtime. That's right. Our good old formula. So this is equal to 100 divided by, oops, my bad, I plugged it in the wrong spot. Everybody makes mistakes. So this is 100 watts. This is 12 joules. We're looking for the time. You cross multiply. 12 is equal to 100 times t, and that's why t is equal to 12 over 100. Or t is equal to how many seconds? 0.12 seconds. Or you could say 1.2 times 10 to the negative 1 second. But who would even say that ever? Some people. An electric drill operating at 120 volts draws a current of 5 amps. So they're telling you the voltage and the current. What's the total amount of electric energy used? Again, they're looking for W. That's the electrical energy. And they're telling 2 minutes. Again, they're trying to really trick you. If you didn't realize that you had to convert this to units, to seconds, then you might be having a hard time with this one. All right, so let's see. 60 seconds per 1 minute. That's really what you're doing, folks. That's 120 seconds. You probably could do it in your head. But it's good to know how to convert units properly. So we're looking for the W equation that has V and I. We don't care about R right now. If it has R, we don't want it. So we're not talking about the old school formula. This doesn't have R. Nice. This has R. Get out of here. Get out of here. So VIT. And you plug in. And you get 72,000 joules of energy, which is, it's a drill operating for 2 whole minutes. It's a lot of energy, but it's within the realm of possibilities. So that's 7.2 times 10 to the 4. All right, here's where I would use scientific notation for sure. We're doing science. You got to do scientific notation sometimes. Number 14. In a simple circuit, a 15 ohm resistor is connected across a 6-volt battery. What is the current in the circuit? So no power mentioned, no electrical energy, just straight up R, V, and I. Hopefully this looks familiar. We're just going to go back to the Ohm's Law. I is equal to V over R. Don't forget, you have a lot of tools in your tool belts now. This is towards the end of our big, long practice sheet with power and energy, but Ohm's Law is still a great, valid equation that we could be using. Don't forget about this equation. It's going to be very helpful when we start analyzing circuits, and that's how you get the 0.4 amps. All right, last question. Whoa. How much electrical energy is required? So they're looking for, okay, so now back to what the sheet is about. Moving 8 microcoulombs of charge. Oh my goodness. All right, so they're talking about charge. What is the physical quantity? What's the letter for charge? We got to use Q. But it's a microcoulomb. Are you kidding me? Micro. Let's see. Even though it says microcoulomb, you're not going to find any micro information on the electricity section. You could have micro anything. Micrometers, microseconds, micrograms. We're looking at the prefixes on the very first page. All right, bottom left. They're talking about micro. So I'm going to use this, the Greek letter mu, and we're going to replace micro with times 10 to the negative 6. All right, I'm just going to replace it. So if it says, I forget what it said, 8 microcoulombs, that becomes 8 times 10 to the negative 6 coulombs. So first of all, instead of like the long word written out like that, I'm going to rewrite it because it's fancy. You get to make a Greek letter, a microcoulomb. And then what I was saying was you just rewrite. So the charge we're going to really use, we want it to be in terms of coulombs. So 8, and then you replace the micro with times 10 to the negative 6. and then you continue, the next thing that was there was a coulomb. So that's how many coulombs it is. Okay, and it's a potential difference of 40 volts. So V is equal to 40 volts. Oh, see, I thought it was going to go back to that long list of equations for electrical energy. But what are they telling you? They're telling some kind of charge and a voltage, and they're looking for energy. Let's look at the reference table. So yes, they're asking for the electrical energy, which is the work, all right? And they tell you the voltage, and they're also telling you the charge. Is Q, oh boy, is Q in any of the equations down here? Do you see a Q anywhere? Q, 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 Q. Nope. Can't use any of these for this situation. So what the heck do you do? Do you have to do like multiple Just relax. Maybe we see a W somewhere else. Maybe these two things together looks a little familiar. Let's look. Does this have W? Nope. W? Nope. What? That? I forgot about that one. Okay. How about, there's a Q over here. Can we use this? No. No W. No W. No W. No W. So don't forget, it's there. That question's there to remind you, hey, we already talked about electrical energy when we did 10.6 voltage. And we talked about like the potential difference and all that stuff. So we're actually going to use this formula. Don't forget, there's a W here, and all these are W too. Okay? So this was kind of like a double trick, because it's saying, hey, do you remember the definition for potential difference? V is W over Q. That's not something else you could use. But also the double trick I'm talking about is this microcoulomb thing. So maybe you found the right equation, but you just left it in microcoulombs. That's not what you want here, okay? So actually, if we wanted to be fancy again, you could cross multiply first, and you come up with a fancy equation on your own for electrical energy. It's the potential difference times the charge. And then we're going to do the potential difference is 40 volts times 8 times 10 to the negative 6 coulombs. That's 8 microcoulombs. It's a small amount of coulombs, 10 to the negative 6. You multiply those two numbers, and you get 3.2 times 10 to the negative 4 joules, right? Because work is measured in joules of electrical energy. All right, and that's how you do that one. So some of those last two, you might have been, maybe a little tricky, but remember, there's always got to be a way to do it, especially in physics. There's always going to be a way. It just takes a little bit of critical thinking, and your teachers are here to support you. So if you ever need anything at all, any help at all, just reach out to your teachers, and I'm sure they'd be happy to help you. All right, have a great day.